Let us look at Lagrange's theorem. Given a group G under an operation star and H being a subgroup of G, where G is finite, let order of H be equal to M and order of G be equal to N. Then N is equal to K times M, which basically means that M divides N. Now, here K is the number of cosets found, either left or right. Number of cosets times the number of elements in the subgroup H gives us the number of elements in the group G. The number of distinct left or right cosets of H in G is called the index of H in G, written as within square brackets G is to H. So in the above expression, N is equal to K times M. N is the order of G, M is the order of H, and K is the index of H in G. So that can be written as order of G equal to order of H times index of H in G. Or we can say order of H divides order of G, giving us the number of cosets, that is index of H in G. Let's look at order of elements and subgroups. For any A in G, the order of the element A, say R, is the smallest positive integer such that A to the power of R is equal to E. In case of cyclic subgroups, order of the subgroup generated by A divides the order of G. That is, R divides N. So, N is equal to R times M. A to the power of N is equal to A to the power of R times M, which is equal to A to the power of R to the power of M. But A to the power of R is equal to E. So, E to the power of M and E to the power of anything is equal to E. Now, all of the above makes sense when order of G is finite. So, if order of G is infinite, some elements may have finite order, some elements may have infinite order. If order of A is finite, the above applies. If order of A is infinite, the above does not apply, since A to the power of infinity is equal to E is not meaningful. So here Lagrange's theorem basically gives us the relationship between the orders of various aspects, that is order of the group, order of the subgroup, order of the elements of a subgroup. Now, very interestingly, if order of G equal to P, where P is prime, then the only divisor of P is 1 and P. So, which implies the only subgroup of G are the subgroup containing only the identity and the group itself. Now, for every A not equal to E, we must have order of A equal to P, because the only divisors of P are 1 and P. Now, if order of G is equal to N, where N is composite, in this, if G is cyclic, for every divisor D of N, there is a unique subgroup of order D generated by A to the power of N by D. G is not cyclic. A not equal to E and order of A is a proper divisor of N, then A generates proper subgroup of G. So let's look at some examples to understand this. Let's take the group containing fifth roots of 1 under multiplication. So let's say that is equal to 1 comma zeta square comma zeta cube comma zeta to the power of 4 under multiplication. Now here zeta is equal to this expression root 5 minus 1 by 4 plus I times square root of 10 plus 2 times root 5 by 4. Order of G is equal to 5 and 5 is prime. Just based on this, using Lagrange's theorem, we can say that order of H divides 5, which implies that the order of the subgroup H is in the set 1, 5. So the subgroups are the trivial subgroups. That is one containing 1 and the second is the group itself. Let's look at another example. Quaternion group. This, as you remember from previous sessions, contains plus or minus 1, plus or minus I, plus or minus j, plus or minus k under multiplication. Here the number of elements, that is order of Q8, is 8. And the order of the subgroup of Q8 would divide the order of Q8, that is 8, which implies that the divisors would be the set of orders of H, that is 1, 2, 4, and 8. So the subgroups are of order 1 is the set containing only 1. Order 2 will be the subgroup containing 1 and minus 1. Order 4 is the subgroup containing 1, minus 1, I minus 1. Another subgroup 1, minus 1, j minus j. And another subgroup is 1, minus 1, k minus k. So these are the 3 subgroups of order 4. And finally, order 8 is the Q8 itself. So the beauty of Lagrange's theorem is that without actually knowing the cosets, we can directly figure out the number of subgroups that will be there and their different orders or subgroups of different orders. So that was Lagrange's theorem. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it. And if you think somebody else can also benefit from it, please do share. That's it for now.